Good morning, dear students. Last class we discussed valence bond theory. Now we are going to discuss crystal field theory. So, in the valence bond theory, the metal undergoes hybridization, ligand donates the electron pair according to valence bond theory. There is a coordinate covalent bond according to valence bond theory. So, what is the postulates of crystal field theory? The bond between, what is the first point? The bond between metal and ligand is purely electrostatic attraction. So, the purely electrostatic attraction means ligand is a metal is a positive charge, it is a vacant orbitals. So, purely just like a what is the electrostatic attraction, right? Suppose M plus L minus. So, there is no bond between metal and ligand, just like a pure electrostatic attraction forces, just like a ionic bond. So, in this one, what is the second assumption? The negative charged ligands are treated as a point charges, the neutral ligands treated as a dipoles. What is the meaning of this one? Neutral ligands, dipoles means suppose neutral ligand is a water. So, neutral ligand is a water, dipoles means it is having the two charges. This is a minus negative charge, positive, negative and negative, right? So, hydrogen is a positive charge, right? So, this is a dipole, dipole means two charges. So, the third point is when the metal atom or ion is free without combination of before combination of ligand, all the 5 d orbitals of the metal atom or ion are equal energy, same energy orbitals. Those same energy orbital generally we call it as degenerate orbitals. So, the d orbitals is having the d block is having the 5 orbitals, that is dxy, dyz, dxz, dx square minus y square, dz square. So, dxy, dyz, dxz orbitals are the lobes, the orbital present in the lobes are present in between the axis, in between the, right. So, in between the axis, this one also in between the axis, all these three are in between the axis. So, in this one the electron density located on along the axis, the difference between these two and these three and these two is electron density located in between axis, or these three electron density located along the axis are these two, right. So, these three are T2g orbitals, these two are Eg orbitals. T2g means it is triply degenerated, that means these three orbitals and doubly degenerated, these two orbitals are same type, these three orbitals are another type, right. So, before approaching the ligand, these are all the 5 orbitals having the same energy. That is why these orbitals generally we call it as degenerate orbital. So, what are the 3 points? Metal ligand bond is the ionic type of bond, electrostatic attraction. The second one is the ligands, the negative ligands treated as a positive, whereas neutral ligands treated as a dipoles. The third one is when the metal ion is free, all the 5 d orbitals having the same energy, those orbitals generally we calling as degenerate orbitals, right. So, the types of orbitals are 5, 3 are in between the axis, 2 are the electron density located along the axis, right. So, the next one is crystal field. The same concept is slowly we are applying into octahedral and tetrahedral complexes. Crystal field splitting in octahedral complex. When metal atom combined with the ligand, so what happens? Ligands are approaching metal atom in the symmetrical manner. Suppose this one is the metal. In the red color, there is a different ligands are approaching towards metal atom. So, what you are doing? You are taking the ligand solution, you are adding the metal atom. So when you add metal atom to the ligand solution, what happens? All the ligands are approaching metal atom symmetrically towards the metal atom. But finally, this is a octahedral complex. That's why how many ligands can approach the metal atom? Only, even though there are lot of ligands in the solution, only 6 ligands are approaches towards the metal atom, right? So when ligands are approaching, there is a repulsion takes between ligand electrons and metal atom electron. So what you are doing, you are taking the ligand solution to that one. What you are adding, metal atom is adding. When you add metal atom into the ligand solution, all the ligands are surrounded by metal atom symmetrically. But how many ligands nearly closest to approach to metal atom? Only 6 ligands can approach the metal atom. That's why we are calling as octahedral complex. Only 6 ligands are approaches towards the metal atom. That is the first point. So what happens when the ligands are approaching towards metal atom? There is a repulsion between ligand electrons and metal electrons takes place. So when the ligands are approaching, metal is having the electrons, ligand can also having the donates the electron. There is a repulsion takes place. Due to this repulsions, this is the diagram. This is the energy increasing level arrow. This is the 5 electrons. When metal atom is free, these 5 electrons are same energy. So when the ligands are approaching, there is a repulsion takes place between these orbital belongs to which one? Metal atom. When the ligands approaching towards this metal atom, there is a increasing energy of d orbitals takes place. That's why these 5 orbitals going towards higher energy. These 5 orbitals are going towards higher energy. When the 6 ligands are approaching towards metal atom, along the axis, right? So which orbitals are along the axis? dx square and z square are along the axis experiences the more repulsions, right? So what you have to understand, there is a metal ligand approaching the metal atom along the axis. Along the axis of what are the metal is having the 5 d orbitals, 5 empty d orbitals. Which orbitals are along the axis? dx square and y square are the along the axis. So ligand approaching towards metal atom through along the axis. That's why dx square minus y square experiences the more repulsive energy. Due to that more repulsive energy, these are going towards higher energy. So this is the energy increasing order. These are going towards higher energy. So the remaining 3 orbitals, what are the 3 orbitals? dxy, dyz, dxz orbitals are lowering the energy. So how much this splitting generally depends upon the strength of the ligand. The splitting pattern depend upon the strength of the ligand. So generally, I told you in the beginning, fluorine, chlorine, bromine, hydroxy, water, sulfide ions are weak field ligand. Weak field ligands means they splits very short distance. So NH3, En, Cn, Co are strong field ligand. What is the meaning of strong field ligand? So the distance between this one is much more larger. The Eg and T2g orbitals are much more larger. So they, in textbook they have given the increasing order of their ligand. CO is the strongest ligand, iodide is the weakest ligand. This series generally we are calling as spectrochemical series. So based on this spectroscopic method they have decided. So in this one, the electrons are, once the splitting takes place. Splitting means, what is the splitting? Dividing of d orbitals takes place. Dividing of d orbital takes place in 2 sets. One is Eg set, the second one is T2g set. Why this splitting takes place in different way? because the ligand is approaching towards along the axis. Along the axis orbitals are which orbitals are along the axis? Dx square minus y square and dz square are along the axis. That's why they are experiencing the more repulsive forces. That's why that increases the energy. So these three orbitals dxy, dyz, dzx are in between the axis. These are which one? In between the axis. That's why they are lowering the energy. How much lowering the energy? So total orbitals are 5, right? You have to write it as a 2 by 5. For this one it is a 3 by 5 delta O. What is the meaning of delta O? Splitting of octahedral energy, right? Splitting pattern in the O means octahedral energy, the delta means the difference, right? Octahedral energy difference, right? Delta O means it is a octahedral splitting, right? The difference between Eg and T2G, generally we call it as crystal field stabilization energy. The energy difference between Eg and T2G, generally we call it as crystal field stabilization energy, right? So how the pattern is, how the electrons are filling in these orbitals. Once the splitting takes place, ligand donates the electron. So up to this, the splitting pattern, the splitting of metal atom takes place. At this stage, ligand donates the electron. Ligand is having the excess electron, it donates the electron, right? So the ligand donates the electron. First electron goes to this one, second electron goes to this one, third electron goes to this one, this orbital. So fourth electron goes to either it may be fourth electron is having the two chances. Either this one goes to this orbital or this can pair up in the first orbital. So there are two possibilities I told you in this one. So D1, D2, D3, first 3 electron goes to the T2G orbitals. The fourth onwards having two possibilities. What are the two possibilities? In the case of strong field ligand, in the case of these strong field ligands, the difference between Eg and T2G are much more greater. That's why fourth electron is going into the T2G orbital. Fourth, fifth, sixth electrons are going into the T2G orbitals. Seventh electron goes to the Eg orbital. In the case of weak field ligand, because the gap between T2G and Eg is very less, 1, 2, 3 electrons goes to the T2G orbital, fourth one goes to the Eg, fifth one goes to the Eg, sixth one comes to the again T2G, right? So the pairing starts from this sixth electron, but in the case of strong field ligand, the pairing 1, 2, 3, fourth electron goes to the again T2G orbital, because the energy gap between Eg and T2G are much more greater in the strong field ligand, right? You have to understand that point clearly. So how the in the case of I explained in the clearly, in the case of weak field ligand, the fourth electron enter into the T2G3 Eg1. That means T2G fill up with 3 electrons, fourth one goes to the Eg orbital. T2G3 Eg2. T2G4, the pairing starts from the sixth electron, Eg2, T2G5 Eg2, T2G6 Eg2, T2G6 Eg3, T2G6 Eg4. This is in the case of weak field ligand. In the case of strong field ligand, fourth electron enter into the T2G. You have to understand the difference between this one, right? So the fourth electron here T2G3 Eg1, but here T2G4, T2G5, T2G6. Once the 3 T2G orbitals are completely filled, then the seventh electron goes to the Eg orbital. The 8th electron goes to the Eg orbital, the 9th electron goes to the Eg orbital, the 10th electron goes to the Eg orbital, right? So why this 7th electron goes to the 7th, 8th, 9th, 10th electrons goes to the Eg orbitals? Because the difference of Eg and T2G are much more greater. That's why the energy difference, this difference is much more greater. That's why the sixth electron cannot enter into the Eg orbital. That's why it can pair up takes place in the T2G level. Pair up takes in the T2G level. Right. So this is regarding to splitting pattern in the octahedral geometry. Splitting pattern in the octahedral geometry. What are the points? Right. So once again, octahedral geometry, what you are taking ligand solution, you are adding the metal atom. Once you are adding the metal atom, the ligands all are approaching the metal atom symmetrical manner. So only 6 ligands approaches the metal atom very closer. That's why you are calling as octahedral complex. When the metal atom, when the ligands are approaching towards the metal atom, there is a repulsion between metal and ligand takes place. Metal electrons and ligand electron, there is a repulsion takes place. That's why the 5 electrons are shifted towards the higher energy state. Right. So when this is higher energy of d orbital. Still there is no splitting takes place. So when the ligands are, so up to this metal, so once the ligands are approaching, there is a dividing of d orbitals takes place. That means the 3 sets going towards the 3 orbital going lower energy side, the 2 orbitals are going towards higher energy. Why this splitting takes place? Because the ligand is approaching towards the metal d orbitals. So ligand, how the ligand is approaching? Along the axis. Along the axis, which orbitals are present? Eg orbitals are present. So these Eg orbitals are much more repulsive, experiences the repulsive energy. That's why that increases the energy. This Eg orbital stability is low because there is a repulsive energy between Eg orbitals and ligand takes place. Why Eg orbitals and ligand repulsive energy? Because ligands are approaching along the axis. Along the axis orbitals are Eg orbitals. That's why these Eg orbital experiences the more energy. T2g orbitals experiences the lower energy. That's why it goes downwards, it goes the upward. This is the energy increasing order. How much energy it is decreases? 2 by 5 delta O. Delta O is splitting of octahedral geometry. 3 by 5 delta O. Some books they have written as a minus 2 by 5 plus 3. That means it is increases the 3 by 4 delta O energy. It is, or you can write it as a 0.6 delta O. That is equal to which one? 0.6 delta O. This is equal to which one? Minus 4 delta O. Minus 0.4 delta O plus 0.6 delta O. Right. So plus or minus indicates the increases the energy, minus indicates the decreases the energy. Right. So the electrons are filling takes place according to strong field ligand is a different strong field ligand, the fourth electron enter into the T2g orbital, whereas in the weak field ligand the fourth electron enter into the Eg orbital. So in the case of, so just in the weak field ligand I am explaining this one is T2g, this one is Eg. So the electron enter into in this one 1, 2, 3, right. The fourth electron goes to the Eg orbital, fifth electron goes to the Eg orbital, the sixth electron again goes to the T2g orbital, seventh electron goes to the T2g orbital, right. So the eighth electron goes to the T2g orbital, right. So this one is T2g, slowly T2g, this one is Eg. So the ninth electron goes to the Eg orbital, the 10th electron goes to the Eg orbital. This is in the weak field. So why this one is taking place? The difference is very less, that's why it is taking place like this. But in the case of strong field ligand, the gap between this one and this one is much more greater. These two are greater. So what happens? First electron goes to this one, second electron goes to this one, third electron goes to this one, right. So fourth electron does not go to the Eg orbital, fourth electron goes to the again T2g orbital, fifth electron again goes to the T2g orbital, sixth electron again goes to the T2g orbital, seventh electron goes to the Eg orbital, eighth electron goes to the Eg orbital, ninth electron goes to the Eg orbital, 10th electron goes to the Eg orbital. This one is Eg, this one is T2g. Why this one is happen? Because the gap is more. Gap is more. Here gap is very less. That is the difference between strong field and how the electrons are. So what is the meaning of pairing? Delta O, if the less than P, P means P is the pairing energy. So if the pairing does not takes place, it results the more, it gives the more high spin complex. If the pairing takes place, generally that gives the low spin complex. So pairing starts means the number of unpaired electrons are very less, that results the low spin complex. Right. Crystal field splitting in the tetrahedral geometry. The difference between octahedral and tetrahedral is, so that is same, but in the case what happens, you are adding the metal to the ligand solution, but the ligand approaching is in between the axis. So what is the main difference between octahedral and tetrahedral? The approaching of ligand. In the tetrahedral, the approaching of ligand in between the axis. So in between the axis, in between the orbital. So what are the in between orbital? dxy, dyz and dzx. So tetrahedron generally we represent as a T2. There is a G is removed. T2 experience the higher energy. So when the metal added to ligand solution, same, the ligand approaches the symmetrical manner, but 4 ligands are in this one. How many ligands approaches the metal atom? 4 ligands approaches the metal atom. So tetrahedron means 4 ligands only, finally 4 ligands approaches the metal atom. So when the ligands are approaching, the d orbital energy is increasing. So these ligands are approaching in between the axis. So the in between the d orbitals are dxy, dyz, dxz orbitals experiences the more energy. Why these orbitals are experiencing the more energy? Because these orbitals are in between the axis, right? So ligand approaching is in between the axis in the tetrahedral geometry. That's why these orbital experiences the more repulsive energy. That's why it increases the 2 by 5 plus 2 by 5 delta O. This one is minus 3 by 5 delta T. T means here tetrahedral geometry, right? Minus 3 by 5 delta T. The remaining is same, right? What is the difference? Main difference, octahedral geometry, the ligand approaches along the axis. In the tetrahedral geometry, the ligand approaches in between the axis. Once, in whichever way the ligand approaches, those orbitals will experiences the more repulsive energy. Those orbitals energy will be increases. That point you have to understand. Right. The relation between tetrahedral geometry and octahedral geometry is the delta T is equal to 4 by 9 delta O. What it tells? The octahedral splitting value is greater than the tetrahedral splitting value. So which one is the greater? Delta O is greater than delta T. Right. So the color properties, VBT does not explain the color and magnetic properties, but CFT explain the color and magnetic property very clearly. So color of coordination compounds explained by CFT. Color of coordination compounds is due to dd transition of electron. One d orbital to other d orbital transition of electron takes place. Due to that one, the electron complexes shows the different color. Suppose for example, if you take the hexa aqua titanium plus 3. What is the name of this one? Hexa aqua titanium 3. Right, this is a neutral ligand. So what is the name of this one? Hexa aqua. Complex is positive charge, neutral you have to write it as a titanium only, right? Titanium, hexa aqua titanium 3. The complex charge is the titanium charge. So it is an octahedral complex because it contains 6 ligands. Oxidation state is the plus 3. What is the electronic configuration of titanium? So 3d2 4s2, right? Titanium plus 3 is the 3d1 4s0, right? So ligand, water ligand approaches the titanium. So the splitting of, I am not writing all these same energy splitting takes place, because tetrahedron, that's why you are writing at the bottom T2G, at the above Eg. So only titanium plus 3, how many electrons are present? Only one electron is present. That one electron present in the which orbital? T2G orbital. So once this T2G orbital H nu, what is the meaning of H nu? Radiation. Once it approaches the radiation, so this electron goes into the higher energy. Which is the higher energy? Eg orbital. So once it goes to the Eg orbital, when it comes back to the ground state energy, it releases some energy. That energy is in the form of different color, right? So that's why the electron is transition from one d orbital to other d orbital. So why coordination complexes are colored complexes? Because the electron is transferred in between the two dr. T2G also metal d orbital, this one also d orbital. The electron goes from the T2G to Eg. So the electron is transition takes place in between the T2G to Eg. That's why we are calling as, due to this electron transition between the dd orbitals, the complexes generally shows the color nature according to CFT. So in the absence of ligand, suppose if you remove the water, what happens? The titanium splitting does not take place. In the absence of ligand, crystal field splitting does not take place. That means the 5 orbitals are same, the splitting does not take place. Once the splitting does not take place, there is no question of electron transition. Once the electron transition does not take place, when it comes to the ground state, it does not emit any radiation. That emit radiation does not emit, it does not show the color. So in the absence of ligand, there is no splitting takes place, there is no showing of the color nature. So anhydrous copper sulfate is white color or colorless, whereas hydrous copper sulfate is blue color. So what are the reason for that one? Because of water acting as a ligand. So what happens if the water is acting as a ligand? There is a splitting of d orbital takes place in the copper ion. So once the splitting takes place, the electron transition takes place between T2G and Eg orbital takes place. dd transition, what is the meaning of dd transition? D means one T2G set, another D means Eg set. So the electron transition takes place. Suppose the electron goes from the lower energy to higher energy. The electron goes from the lower energy to higher energy. So when it possible, when the electron absorbs the radiation, it goes from lower energy to higher energy orbital. So this electron goes from the lower energy to higher energy. The electron does not stay at higher energy at longer time. It comes back to the original one. Once it come back to the original one, come back to the original ground state, so what happened? It releases some energy. Releases some energy. This released energy is, if they follow in the visible light, it shows the color. That is a reason for color nature, right? So the main reason for is the electron transition takes place in between the dd orbital or T2G and Eg orbitals. So what are the limitations of CFT? What is the limitations of CFT? CFT considered as a metal ligand bond is purely electrostatic. The metal and ligand bond is purely electrostatic, but this is not true in all the complexes. Ligands are point charges. Anionic ligands should exert more. That means the ligands, negative ligands are point charges. That's why these negative ligands should exert more splitting. But if you see in the spectrochemical series, these are kept at lower end. The negative ligands are kept in the lower end. Strong field ligands are most of the strong field ligands are neutral ligands. The negative ligands are kept at lower end in the spectrochemical series. So CFT that metal ligand always it does not considered as a ionic bond. The second one is the anionic ligands are found at lower end of spectrochemical series. That is not always true. So these are lower end, this one is higher end, right? So the strongness increases, right? This is about crystal field theory. This completes the coordination chemistry. So once again CFT, the splitting takes place, right? Without what is the main points? The splitting of d orbital takes place. That's why we are calling as crystal field theory, crystal field splitting, right? So why splitting takes place? Ligands are approaching towards metal atom, that's why splitting takes place. If the ligand approaches along the axis in octahedral takes place. Octahedral, the ligands approaches along the axis. In the tetrahedral, ligands approaches metal atom towards the in between the axis. That is the difference between octahedral and tetrahedral. So in between the axis, that's why T2G goes to the higher energy, EG goes to the lower energy. In the octahedral, the ligand approaches along the axis, that's why EG goes to the higher energy, T2G goes to the lower energy. That is the difference. So the electron transition takes place between these two orbitals. That's why the coordination compounds are colored compounds. Coordination compounds are colored compounds. In the case of strong field ligand, the difference is the EG set and T2G set is more. That's why 4th, 5th electrons are pairing takes place in the T2G. In the case of weak field ligand, 4th electron goes to the EG level. This is applied to the same strong field, weak field also applies to tetrahedral complexes also, right? So this is about this CFT beautifully explain the color properties and magnetic properties very clearly. So the number of unpaired electrons related to magnetic property and also the color properties also can be explained very clearly. There are a lot of merits. There is some few demerits. The demerits are rectified by the other new approaches which is not in our syllabus. The ligand field theory, the LFT ligand field theory and MOT molecular orbital theory can explain the demerits of crystal field theory, right? So this completes the CFT and this completes the coordination chemistry. Thank you.